Okay, everybody, welcome to the March OCGS Technical Luncheon, coming to you virtually. Today, we're going to have a talk from Dr. Hansel Gonzalez, the theory and applications of wave equation-based AVO seismic inversion, known as Web AVO. Before we do that and hear from him and the co-founders of the company, Delft Inversion, I'd like to thank the sponsors of OCGS for continuing to support us through this 2021 continued pandemic year. Things are improving. And also like to bring everybody's attention, hopefully you've seen this already, but we got a few events coming later this month and then April and May. So at the end of the month, the 26th, there's the Spring Clay Shooting Tournament. And just a reminder, you don't have to be a member of OCGS to participate. For more details, you can go to the OCGS site if you want to do that. On the 21st, we're going to have Stephen Hubbard from the University of Calgary, who's an APG Distinguished Lecturer this year, giving a talk. And then in May, Jeff May, retired Chief Geologist at EOG and affiliate faculty at the School of Mines, Colorado. We'll be talking in May. And then our first in-person course will be the last week of May, and it'll be reservoir engineering for geologists. So details down there as well. Lunch provided. And you can see more details on the OCGS site for that as well as the sign up. So now let me briefly give a brief bio for Hansel and then let him take over from there. So Hansel has 20 years of experience working in reservoir geophysics. He joined the industry at Veritas DGC in 2001 after graduating from the University of Oklahoma with his master's, where he worked underneath John Castagna, excuse me. His career has been focused on seismic reservoir characterization, dynamic and static at all stages of field life for both service companies and operator perspectives. Hansel's PhD work consisted of constraining the dynamic model via the use of 4D seismic on a deepwater West African field, he also holds an Executive Master's of Management and Energy degree, jointly issued by the Institute of France du Pétrole and the BI Norwegian School of Management. His experience ranges from basin-wide exploration and the development and production of both conventional and unconventional resources worldwide, and now venturing into the quantitative seismic applications for the geothermal industry, while being based between the US and Northern Europe. Hansel joined Delft Inversion in 2019 and is currently their operations manager, where he leverages his experience to apply the next generation AVO technology, Web AVO, to improve and increase the range of solutions provided by the quantitative seismic methods to oil and gas and geothermal operators. So with that, I will switch over to Hansel's presentation and let him take over from there. It's all yours.
All right, thanks, Raleigh, for the introduction. First of all, I wanted to thank the Oklahoma City Geological Society and their sponsors for having me on today. As an Oklahoma Sooner graduate, it's always nice to touch base back with friends and colleagues back in the state of Oklahoma. And as Raleigh mentioned, we also have with us two of our three co-founders, Dr. Panos Doulgeris, who is currently the managing director, and Dr. Peter Hathinger, who is the director of R&D. And with that, let me go ahead and start with the slides that you can already see. The title of my talk today is A Theory and Application of Wave Equation-Based AVO Seismic Conversion, also known as Web AVO. The agenda for today is going to be quite simple. We're just going to talk about an introduction to Web AVO as a unique and proven technology. Then I'm going to dive into some of the technical details behind this particular inversion. And then we're going to end up with think about 4 or 5 case studies and applications. So why is Web AVO a unique technology? First of all, WebAVO stands for Wave Equation-Based AVO. Peter always mentions that he gets the question if it's a web-based AVO, and not quite, it's a wave equation-based. And this is unique in the sense that all wave propagation modes are considered, not just the primaries like regular seismic inversion, but also we take into account the multiples, the mode conversions, and the transmission effects that occur in the subsurface when acquiring seismic data. Another particular aspect of our inversion is that it is not an extension of Zoeppritz-based inversion models. We went back all the way back to Hooke's law and Newton and reparameterized the inversion in terms of bulk modulus, the inverse of bulk modulus, sorry, which is we call compressibility, or kappa, the inverse of the shear modulus, which is designed as the shear compliance, or M, and of course the bulk density, or rho. Couple of the key things to remember about WebAVO is that the compressibility is about 3 times more sensitive than the fluid change to the acoustic impedance, so it's very useful whenever you're trying to get fluid details within a tighter matrix. And the engine can be applied in 2D, 3D. We have a stochastic version in the works. We currently do quite a bit with 4D time-lapse, and we also work with converted wave data sets. And the image that I have here on the left is from an example from the East Mediterranean, and all I'm doing is comparing the acoustic impedance versus shear impedance of a sand that has a gas and oil and water saturation versus the compressibility and shear compliance. The top cross plot, we have the shear compliance on the x-axis, and we have the acoustic impedance on the y-axis. And the color is blue for the water-saturated sand, and red for the gas-saturated sand. We see that there is indeed some separation between the two clouds of data. However, if we are to try and identify, to separate the gas-saturated sand from the water-saturated sand, we need both acoustic impedance and shear impedance, and we would still have a band of where there is some significant overlap. And that's and we've been working with this in seismic reservoir characterization for decades. However, if you look at the same data points in terms of compressibility on the Y and shear compliance here on the X, you see that the lithology that the water-saturated sand and the shales plot along this axis, and then the compressibility is very, very sensitive to the porphyry and added porosity. So as soon as you have a little bit of gas, your compressibility is going to shoot up, and you get a much larger dynamic range of your water saturation from the actual seismic. This is, of course, at a well log scale, but it will be showing you, I think, no, it will be showing you in the seismic scale as well. So let's go to the next slide. Okay, I talked about why WebAVO is a unique technology. Now let's talk about it being a proven technology. The company that derived WebAVO has been around for 8 years, and as of right now, the end of first quarter of 2021, this is about the international footprint of where we've had done our projects. The oil and gas projects are in the teal. The geothermal project is in the green, which is right now it's just starting close to home in the Netherlands. And we have a couple of carbon capture and underground storage projects in Montana and in the North Sea, Norwegian North Sea as well. So what are the applications that we have, that a lot of these projects have been? Is prospect de-risking, and that goes into the fizz gas identification along with carbonate reservoir quality. And I will talk about the fizz gas issue in a particular case study, because that is maybe not so much for Oklahoma reservoirs, but definitely for Gulf of Mexico and Northwest Australia, it's always been a bit of an issue. We're also able to characterize fluids in tighter clastic reservoirs, or in tighter reservoirs in general. We do fluid and pressure monitoring with the 4D. If you remember, the shear compliance, the M, is the inverse of the shear modulus, so it is completely insensitive to fluid. Normally, we try and do that with other attributes such as mu rho, but mu rho has the pesky rho, which of course is going to have the effect of the fluid in there. We're also able to do to improve reservoir delineation. We push the boundaries of resolution, especially on the low side, and I will talk about that a little bit further. And we're able to do improved lithology and porosity characterization in high contrast settings. So airs with complex overburden, carbonates, etc. And last but certainly not least, we have a very, very cool tool that we call the wave equation-based interbed multiples investigation. We're able to pre-inversion to investigate which geological layers are the ones causing multiples, transmission effects, etc. So we're able to optimize the inversion window, and as well, after an inversion result, we can take a random inversion location trace, and we see where the inversion predicted multiples, mode conversions, and etc. And last but certainly not least, these are a few of the companies that have used WebAVIO up to now. So let's talk a little bit about the evolution of AVO. We all know that AVO started with intercept and gradient. It was a simple geological interface between two half spaces, and the wave propagation was reduced or approximated by a single primary reflection, and it gave us a classification of different AVO classes 1 through 4 that we all know. And it was basically used for qualitative screening for potential reservoir. This is all fine and dandy. We still use it in certain cases, but then we moved on in the technological evolution, and we came up with the AVO inversion, which is more state-of-the-art or the most used technology right now. Instead of having just one geological interface, we have a stack of geological interfaces, and it's commonly based on the linearization of the Zoeberts equations using Shuey, Aki-Richards, Fati, name your flavor. The wave propagation is approximated by a superposition of primary reflections, which allows us a slight detuning over the seismic wavelength, and we end up obtaining reservoir properties in terms of impedances: acoustic impedance, shear impedance, or acoustic impedance, and VPVS. So we believe that WebAVO is the next step forward. And the reason for that is that instead of looking into geological interfaces, we're looking into stack of geological units. It's actually layer-based. We don't go back to Zoeberts, but as I mentioned earlier, we go back to the original physics of Hooke's law, Newton, and we solve the full wave equation. Hence, it is accounting for the primaries, multiples, mode conversions, and transmission effects, causing a detuning over the full interval. And the other interesting thing is that we're estimating the reservoir properties in terms of compressibility and shear compliance. And we do have a paper published by our third co-founder, and where he explains the actual uplift of using compressibility and shear compliance versus AI, VPVS, etc. I'll explain a little bit more of that as we go along. So let's go to the next slide. All right. So how does the iterative WebAVO seismic conversion workflow work? Pretty much. We start with an incident field, a low frequency model, and a wavelet, and a migrated seismic gatherer. The input for a WebAVO is a migrated NMO corrected seismic gatherer. Nothing more, nothing less. Of course, there's going to be a lot of flavors in terms of if you want preconditioning, but we can discuss that a little bit later, and I'm expecting a lot of questions in that regard. But the first iteration is always a linear input. So we have an incident field, a migrated seismic gatherer, an AVO inversion engine, and boom, we get an elastic set of reservoir properties, like we do with any other AVO inversion product. However, what we do differently is that we use the wave equation to add a higher order of scattering. And from that, we create, or rather, we update the total field. At that point, we use the updated total field and the migrated seismic gatherer to run the AVO inversion again. And we keep running this this set of iterations until the whole machinery converges. And what I mean by that is that simply we keep running the iterations until the properties are no longer changing, until the compressibility and the shear compliance are no longer changing. What's interesting here is that many seismic inversion algorithms force the inversion to converge to the properties at the control wells. We do not do that. We just let the algorithm iterate until it finds its own convergence. Normally, we can do up to 10, 15 iterations in a synthetic case, and if we have actual noise in real seismic data, it might go down to 10. Of course, for carbonates and other areas where we do have a lot of elastic chatter within the seismic data, I've gone up to 12 and 15 iterations. So whenever I talk about a loop, an outer loop, this is what I meant. If I say we're looking at an example here that has 10 loops or 10 iterations, we went and added up to 10 orders of scattering of the wave equation into the inversion. Great. So with this in mind, let's look at a synthetic example, which is a carbonate case in a very high reflectivity environment. This is a synthetic example based on real logs from the North Sea. We have a carbonate reservoir embedded between two anhydrite units. So of course, we're going to have extremely strong changes in elastic properties along these geological interfaces. We're using a low pass 4 hertz low frequency model from the logs, and then we're going to create 2 synthetic data sets. One based on traditional SHUI, which is just regular primaries, and another based on the Kennett method. And just just a quick disclaimer, since we have such high velocities in the anhydrite, we're only able to go up to 18.5, 19 degrees before we hit the critical angle. So that's going to be the upper limit of what we look. But of course, if we're looking at elastic effects at multiples, mode conversions, et cetera, we're always going to look at the furthest angles because that's where they're going to be more prevalent. So let's go to the next slide. Great. Let's go ahead and look at the linear modeling, the SHUI model for this geology. I have it here, a little bit of an extra space underneath the primaries window, because since we're looking at multiples, mode conversions, et cetera, we're going to have slower events coming underneath. So I'm going to toggle for a few times the linear model between the linear model and the wave equation-based model, just to see the actual differences. Here we have the linear model. Here we have the elastic wave model. First thing that we can see is that we have the coda, which is all the events that were slower than the primary PP time in this window. So of course, whenever we have actual acquired seismic data, we have the sum of the primaries and the coda for the whole section. So let me go back again. We can take a look at around, I think it was around here, and see how we see the difference. See, we have linear modeling, we have the wave equation-based modeling. Linear modeling and the wave equation-based modeling. The purpose of this is to illustrate if we have actual seismic data acquired over this geology, a linear inversion would only match the well logs if it looked like this, if the seismic looked like this, the seismic gather. But the seismic gather is actually looking like this. So it is very likely that the linear inversion is going to predict a different set of properties than a scheme that understands that all the differences between these two are because of elastic wave propagation modes. So I'm going to click a couple more times, and then we're just going to go ahead and look at the difference here. So first of all, let's just take the usual difference, see what that shows us. We see a small set of travel times because the linear inversion is using the timing calculations from the wave parameter, while we're using the wave equation based. Now we see mode conversions. We see that they have some move out because mode conversions are going to be P, S, P, P, or P, S, S, P. So you're going to have the S velocity propagation, which is going to slow them down, and hence you see a bit of the move out here. If you focus on these are going to be most likely the transmission effects. These are amplitude differences in the deeper section because of the carbonate anhydrite units, of course. And last but certainly not least, we see that there's integral multiples all over the place, but these are quite difficult to highlight as they're propagating at a similar speed to the primaries. And this is definitely, a lot of this is going to be interpretive, and I will show you that in the next set of slides. Great. I mentioned in my second slide a little bit about the wave equation-based integral multiple investigation. So here is a panel of a WebIMI for a linear model. So the way that you look at this is more like a VSP field. We have this axis is the depth, and this axis is time. So we're actually putting both realms together in the same image. Here we have the compressibility log that we saw before. Here's the top of the anhydrite. Here's the top of the carbonate reservoir, and here's the base of the second anhydrite. So the way that this would work for interpretation on the linear modeling only would be that we have an incident field propagating down. It sees an interface here at the top of the anhydrite. So boom, it's going to reflect and it's going to go back to the surface, and that's what you're going to see at your geophone. If you have a transmitting data, transmitting wave still going down, you're going to hit here. The top of the carbonate, you're going to reflect. The base of the carbonate, you're going to reflect, etc. And you're going to go ahead and add that up. This is what this is just the field without any multiples or any other mode, any other elastic propagation modes. If we go ahead and use the full elastic modeling, we see that the field, even just the P field here, is a lot more complex than the P field here in the linear modeling, and because a lot of the energy is going to be bouncing within the two anhydrides and the carbonate with a number of paths. It could be 1, 2, down, up, and then down. So there's going to be just a lot of different bouncing up, and you see that by the way that this is a lot more complex than what you see in the linear modeling. Since this is a fully elastic exercise, we still have the S field here. We don't normally acquire PPPS data, but of course it is already built in, which is why we can easily apply any kind of converted wave data into the inversion, which usually strengthens the result of the shear compliance. So let me go ahead and show the interpretation of the primaries here on the P wave. We see the interpretation of the primaries on the elastic field still holds as it did before. However, let's take a look at all the other modes. Here we have different ways of bouncing within the anhydride and the carbonate, which is giving us interbed multiples. And this is what I meant, that we are definitely able to do an interpretive approach to this. But we are definitely seeing that we can actually pick different ray paths for bouncing within this anhydride and carbonate section that you couldn't necessarily pick up here in the linear model. So here we have the interbed multiples. Here we have an interpretation of the mode conversion. So the way that this would work is that this is a P coming down. At this reflection, it converts to an S, continues as an S, continues as an S, it bounces as an S again, and then at the end, it bounces back to a P, and we actually record it in our geophone, in our PP geophone at the surface. So a lot of fun and games to be able to see this, but it actually gives you a lot of understanding of the different elastic propagation modes within the subsurface. And since WebAVO works within a certain window, and it works modeling that window, understanding the Web IMI as shallow as you possibly can will allow you to optimize that window of inversion, because you don't want to miss a model that you might have shallow that might be giving you some elastic effect down at the reservoir. So with that in mind, let's take a look at what happens if we invert the full elastic synthetic that we created for the same model, the anhydrite, carbonate, and the anhydrite, with the two modes. We do the linear inversion, which would be a sparse spike inversion, and we do the elastic wave equation-based inversion. Let's focus first on the residuals on this panel. This is the residuals. So the input data, the inverted seismic minus the predicted seismic, and we do it for both here, and we magnify it by 10. We see that the linear inversion is not able to explain the data. We see that there's move out and there's chatter. There's probably multiples and mode conversions again here, because the linear inversion is only looking for primaries. If we look here at the elastic wave equation, we see that there is noise for sure, but there is not definitely as much of a coherent residual as we see here in the linear inversion. So that's giving us something to start off with, that the wave equation-based inversion is solving for the seismic better than the linear inversion in this case. So let's take a look at the carbonate reservoir here. We see, a sparse spike inversion is doing a fine job. However, we are seeing that the predicted compressibility at the carbonate is about 50% of the amplitude of the true of the log. So if we were to make a calculation on porosity or anything else, we would be 50% off one way or the other. However, when we look down here at the prediction of the compressibility from the WebAVO inversion, we see that the match is much better. And last but certainly not least, we also notice that the sharpness of the boundaries is a little bit better within the WebAVO scheme, especially down here at the base. It's very common if we have a very noisy seismic layer, the overburden, you expect your data underneath to not be able to be resolved as well. However, WebAVO is actually still giving us a decent behavior, a decent prediction for compressibility in the area that's just underneath the anhydrite. And this is and that leads into what I'm going to talk to you here, the spectrum extension. Here we have the results for the linear inversion and spatial wave numbers and amplitude. The seismic bandwidth is measured here in between the dashed lines. The log, the full spectrum log, is in the blue, and the inversion, the resulting inversion for the linear inversion in this case is in the orange. If you see here, we see an okay job. It's definitely not a bad result, but we see there's not enough a match here at the lows, and we see that there could be some improvement, especially here in this first part of the bandwidth. If you go straight to the elastic, the Web AVO inversion, we see that we are actually increasing this orange to match the bandwidth of the well log here in the low very well. So this gap between the low frequency model and the lower spectrum is being minimized. And we also see a much better behavior in this area as well. It may be a little bit better in the higher frequencies, but definitely the biggest improvement is in the lower part of the bandwidth, which of course is what's going to get us closer to the actual absolute numbers. Excuse me. If you look at the shear compliance, in the shear compliance there is an improvement with Web AVO, but it's not nearly as good as you get with compressibility, and that is currently part of our. And that's one of the reasons, if you have PS data, our current research and case studies indicate that it seems to be helpful to use that data to be able to match these two better here in the Web AVO, and that's also part of research to try to improve this as well. But it's still a better result than what we were getting with the linear inversion. However, it's very crucial that we see this improvement in the lower part of the compressibility. Right, certainly something that I never like to forget, especially for crowd back in Oklahoma and the mid-continent and the onshore U.S. Seismic geomechanics. AVO inversion, we know, is a link between geomechanics and geophysics, just because of the definition of elastic properties. And we all know in this audience that geomechanical understanding of the subsurface is very key for the optimal stimulation of tight reservoirs. We know that. We also know that the geomechanical understanding of the subsurface is very important also in seismicity hazard analysis for brine reinjection projects and geothermal projects, because a lot of the geothermal that we're looking at is a doublet. So you have a producer injector pair where you just recirculate the water. And we all know how Oklahoma has been subject to earthquakes in the recent past because of the reinjection of production water. However, geomechanics from AVO inversion is traditionally seen to be challenging because you normally need a reliable density to be able to get Young's modulus. Since we need Young's modulus and Poisson's ratio, to get Young's modulus, we need the density. If we look at the equation here, we see if you have acoustic impedance and shear impedance, you still need the pesky density term here. If you have Landau-Ramiro, you still need the pesky density term here. However, if you look at Young's modulus in terms of compressibility and shear compliance, we don't need to estimate a density, and it's a linear relationship. So we are expecting to have a much more robust Young's modulus that we could use for geomechanical analysis. And not only that, we also saw from the previous slides is that any areas with significant overburden, like we have definitely on the in the onshore US, you'll have improved results because we're taking care of all those multiples, transmission effects, and mode conversions in the inversion that would likely be affecting your linear inversion result. So for seismic geomechanics, I believe that Web AVO is a very interesting way forward, just because of these two effects. And we're currently working further on this, but I always like to point it out. So let's go to the next slide. Right, I finished the first couple of sections, just the introduction and the technology. So let's go ahead and discuss a little bit on the case studies. The first case study I'm going to talk about is mapping of hydrocarbons in a low porosity gas reservoir in the North Sea. Then I'm going to talk about the fizz gas identification case in the Northwest Shelf in Australia. Later, I'm going to discuss a little bit on the onshore carbonate porosity prediction paper that I presented at SEG last year. And then we're going to talk about the use of Web AVO in a Dutch geothermal play. So let's start off with the North Sea data example. I know this is not exactly offshore North Sea. It's not exactly related to what we might see in Oklahoma, but it's super interesting because of the target depth here is 4 kilometers, but we only have 3 kilometers of offset. So we only have up to 1921 degrees of angle, and we have an extremely tight reservoir of 8% porosity. This was done in the early days of the company, back in 2014-15. It was a single well used for calibration and background, and the objective here is that Wintershall wanted to detect and delineate their gas sands, and this was published at the EAG Madrid back in 2015. So here's a seismic line, an arbitrary seismic line around the southern Wingate block and the northern Wingate block. If you look closely, you might see the proposed well trajectories here in red, and these subtle amplitude anomalies are here at the terminations at the unconformity. You know, you can kind of see them, but not really. So let's go ahead and see what the web AVO inversion looks like. Here we have the compressibility result, and first thing that we see is that we do see a nice high compressibility here where the projected wells are expected, and even one here a little bit further to the side. I must note that high compressibility, we're looking at the opposite of like Landerer and Muro. If it's very compressible, it's very likely has a lot of porosity, and it has a hydrocarbon in it. So that's why we use compressibility, because of that 3 times more sensitive that I will explain in this slide as well. The other disclaimer here is that Wintershall did note that the northern side did had a little bit of a time depth conversion issue, but they assure us that this is actually going through these. We also note, and people always wonder, we have a lot of very high compressibility layers around here. And this is because the source in this area of the North Sea are coals. So the coals are very, very compressible. But if we had a little bit of extra offset, and we were able to get a good shear compliance, the shear compliance would be able to indicate us extremely easily where these coals are, because the shear compliance is coals and shear compliance are very, very they show each other up very well, as we've seen in Asia Pacific and in Australia. So let's go ahead and just show the Wintershall ended up drilling these 2 wells. So here you have the gamma ray, and here you have where they expected to have the gas, as well as here 1, 2, 3. Even you have a little bit of hint of the toe at the toe of the well of this final gas sand. So we discussed, I'd mentioned a couple of times about the sensitivity to pore fluids, that compressibility is about 3 times more sensitive than acoustic impedance to a fluid. So let's prove that. We do this experiment with pretty much every project, and it varies, 2.5, 4 times, it just depends, but it really does converge at around 3 times more sensitive. So the reservoir that we're looking at here is at about 4 kilometers of depth. It's very tight, 8% porosity. The PVS and rho defined as this for the water saturation. And what we did was a simple Gassman calculation. Here we have the water saturation on the x-axis. So we have 0 water saturation, 100% theoretical gas here, 100% water saturation, no gas here. And on the y, we have the relative change with regards to water saturation. So the relative change of the amplitude. So here, of course, where we have water saturation, it's changing 0% because it's looking at itself. If we look at the acoustic impedance, which is the red line, we see that once we go ahead and fill that 8% porosity sand with gas, the change in acoustic impedance you're seeing from the acoustic impedance is about a little less than 6%, 5.5%, which is within definite the range of error that you might think for an AVO inversion, a traditional AVO inversion. However, if you look at the same plot with the compressibility, you're seeing that the compressibility is changing almost 19% when you're going from 0 gas to 100% gas. An 18% change in the compressibility would definitely jump out at you in your section a lot more than 5%, and you would be more inclined to believe that it is not just an error. And so this is the kind of analysis that we do, and we do converge that compressibility is about 3 times more sensitive to changes in fluid than just the acoustic impedance. Great, so let's go to the one slider that I have on the fizz gas identification. This was actually published by Woodside Petroleum, where they actually did a very nice analysis comparing our inversion along with the deterministic inversion and a stochastic inversion, and you can read that in the February 2020 edition of The Leading Edge. I believe that the image on the cover of the magazine is also from this paper. And what happened here was as follows. Woodside drilled well C, with live gas off of their Lander Row map. And well A was not drilled yet. They went ahead and used this Lander Row map that shows you low Lander Row should be high gas saturation from their analysis, and they drilled well A in a similar amplitude of Lander Row. However, well A came up residual gas as opposed to a full gas, and you can see that here. Here we have well C. We have full gas saturation, and we have live, and we have the Lander Row amplitude, and here we have well A, where we have very low gas saturation, and we have not a completely dissimilar Lander Row response. So they came to us and they asked us for a WebAVO inversion over their area. We were only given well C, and we produced the usual suspects: compressibility and shear compliance. And this is what the map that we got. So we have at well C, we have live gas, which is great, which is what they were expecting. Well A came up with a definitely less compressible compared to well C, which matches their interpretation, which matches what the well gave them already. And interestingly enough, this further south prospect or feature completely disappeared in our compressibility map. So Woodside did not go ahead and drill that. So this is just an example, a very nice example, I would say, where the sensitivity of compressibility to fluid was able to add significant value to Woodside and their operations. If you also notice, you see that the feature up here has a little bit more granularity to it than the feature here in the Lander Row. So since they're expecting to be all the same channel valley, same porosity thickness, and same geologically basically the same container, this might be attributed to maybe we're seeing differences of saturation here at the edge of the feature. But that's up to interpretation and yeah. So let's go ahead with the next slide. Great. Let's talk about a little bit about the onshore carbonate porosity project out of Kurdistan. We all talk about the carbonate, and about whenever anybody proposes a carbonate inversion, that carbonate inversion is more difficult because it is less sensitive to AVO and it has significant elastic contrast, and that's absolutely true. So with that in mind, let's go take a look at the reservoir facts of this project. It's an onshore Middle East 3D data set in the Zagros Fault Belt in this area of Iraq. It's a Cretaceous dolomite and limestone reservoir, and it has less than 10% total porosities. It is an oil reservoir, and the fracture porosity is a key reservoir component. So here, seismic porosity characterization is the goal. So let's take a look at quick cross plots. Just a quick disclaimer: this project was a feasibility, so the full rock physics, massaging, and everything was not fully done here. It would be done in a follow-up. But here we have three cross plots. We have acoustic impedance on the X, with porosity on the Y, and colored by water saturation. In the middle, we have shear compliance, and the X and porosity on the Y, and we have kappa here on the left. On the right, we have kappa on the X and porosity on the Y, all colored by the same. We see that there is, especially considering noisy data through a carbonate section, we see that there is a decent correlation between porosity and acoustic impedance, porosity and shear compliance, and also porosity and compressibility. However, if you look closely here, you see that these points at 10% porosity do have a little bit of saturation, so they're shooting up from the trend. So you do have a trend that basically, if you have a brine trend, it would be a good correlation, but it would be but as soon as you have a little bit of oil here, you are going to separate from that. So from the log brace cross plots, all three, AI, M, and kappa, all seem to be adequate porosity predictors in this section. However, in a carbonate section, we're expecting the acoustic impedance to not be as accurate than what we would expect from WebAVO. So it might turn out at the end that the shear compliance and the kappa would be better attributes, inversion attributes to use for the prediction of their porosity. So here's a quick QC panel from well A. Here we have the volumetrics, the water saturation. Here we have the kappa. The log is in the black, and the inverted log and the inversion is in the red. There is definitely a bit of a resolution issue because there are high velocities here compared to the frequency of the data, but that's what that is. And here the same for the n. And here I have the residuals. I have the blue is the input stack seismic trace. The red is the synthetic seismic trace predicted by the inversion, and the residuals are magnified times 3 just to get any kind of a color in between, because you see that the inversion is doing a very good job of predicting the seismic. And here we have the same comparison, but I separated it here into gathers. So here we have the seismic gather, the synthetic gather, and the residual, and how we have the partial stacks. The full stack, seismic gather, synthetic full stack gather, and the residual. The same for the near, and the same for the far. So we are doing a very good job of predicting the seismic here. And last but certainly not least, after the project was concluded, here we have a comparison of WebAVIO result versus a linear result that the operator had procured. So here we have another well. I honestly don't know. I don't think this well was given to us, but here we have the zone of interest. And here we have the acoustic impedance and the VPVS from the linear inversion. The blue is the acoustic impedance and VPVS log at that well, and the red is the prediction from their inversion. And here we have the compressibility and shear compliance from our WebAVIO inversion. Again, the greenish is the log, and the red is the inversion result. There is an issue again with resolution because of the high velocities that we have here, but comparing the results, it does show a marked improvement with the WebAVIO inversion. WebAVIO was able to obtain very good property match at the wells, and we also know that the residuals from the WebAVIO inversion are very reasonably quite low. So WebAVIO derived kappa and n would be ideal to perform this 3D seismic porosity estimation in this case. And this is a project that we'll be coming back to do for the full field and to be able to obtain a porosity cube for this operator's development plans. So I think I have just one more case study, which would put me a few minutes over time, so apologies for that. So this is something that I presented at the Geothermal Research Council annual conference last year, and it's titled "The Use of Wave Equation-Based AVO Inversion, Rock Physics, and Mechanical Earth Modeling for Reservoir and Geomechanical Parameter Characterization in a Dutch Geothermal Plant." A little bit wordy, but hey. The key here is that all data was obtained through public repositories. In this case, nlog.nl. The target reservoir here is the Upper Slotted information, which is also known as the Rotliegend. If anybody remembers anything about the Groningen field in Holland, or the Groningen field in Holland, the giant gas field, that is also Rotliegend, the reservoir. We have 2D seismic data. It's migrated, NMO corrected offset gathers, and RMS velocities, which the key here is this. There was no significant pre-processing done. There was no processing with any kind of QI. We just took it off the shelf and threw it into the inversion because we're trying to simulate the options that a geothermal operator would have to try and cut costs. We don't want to have 6-12 months of reprocessing efforts to be able to get this kind of results. We also had core-derived Poro-Perm data from the same formation. And we had data from 6 wells. We had the regular data here and P-Wave Sonic in the area of interest. And as it's very common, we had to go outside of the area of interest, here just a little bit north of Amsterdam, to get 2 wells with S-Wave calibration that we then applied for the wells here in the area of interest. And here is an image of the scanline that we used, that we're showing in this particular example, and the zoom that we are doing where our images will be shown. So just a little bit about rock physics. I'm comparing compressibility versus porosity and acoustic impedance versus porosity. These two are kappa versus porosity, and this two are acoustic impedance versus porosity. The upper 2 cross plots are in situ. The Rotliegend is known for always having pockets of gas and little bits of gas here and there. So it is of interest of these geothermal operators to actually kind of have an idea of where to expect the gas, not to produce it, but just to be able to prepare their wells for it. And they also did flow substitution, and we created brine-only trends. So the first thing that you see is that we notice that you have a gas effect here. And the gas effect in the here in the compressibility, the gas effect here in the acoustic impedance is not nearly as significant as it is in the kappa, which goes back to the whole conversation about compressibility being 3 times more sensitive to fluids, the tighter to fluid than acoustic impedance. So what we ended up doing is that we created a kappa porosity trend with the brine, and then once we defined that there were any ungeological porosities, we tried to highlight that as a gas zone. We could have done this with compressibility and shear compliance. However, my goal was to try and simulate what would a geothermal operator want to do if you're trying to go ahead into an area, you want to get porosity and permeability models that have a little bit more information than just using a handful of wells. You probably won't want to go ahead and do the full WebAVO with, might not even have gathers in many cases in this area. So kappa is the full stack product from us. So I wanted to focus it on that. So we ran the inversion, and these were the results on the line. Here we have the input seismic data. Here we have the inversion predicted seismic and the difference in residuals, and the scale is exactly the same. We see again the seismic is doing a very good job of the inversion is doing a very good job of predicting the seismic. Here we have the compressibility and the shear compliance. So we see that it matches the wells pretty good with the kappa and fine with M. Again, we didn't do absolutely any preconditioning on this. We also noticed that, of course, we can always do a better job of picking the ligand with the either the relative or the full inversion kappa, because we see that the black lines are not entirely matching where we see the higher compressibility sand. And we also calculated porosity, and I used a proto-perm relationship from CORS to be able to get a permeability volume as well. It is not our intention to substitute what geomodelers would do, but we do wanted to go ahead and give a 3D volume from the seismic that would be able to serve as a soft constraint for the geomodeling efforts to be able to get permeability as well as porosity. And as I mentioned before, drillers in this neck of the woods, they want to know where the gas is, or if there's any variation of where the gas is, so we created a gas flag as well. And last but certainly not least, with the equations that I showed you just before the case studies, we created Young's modulus and Poisson's ratio. This is still a work and study. This is work with the Dutch government, so we are working this a little bit further. We should be able to present something in EAG this year, but this is what we presented last year, the first part of the study. And these are also the results at the well location. Here we have the compressibility, the shear compliance, the porosity, the permeability, the Young's modulus, and the Poisson's ratio. The well log is in black, and the inverted property is in the color as changing per property. There were really good results for kappa were achieved. We normally see that in every case, kappa is very, very stable. We see that that the shear compliance does have results, does have areas of improvement that could be achieved with a little bit of pre-processing, maybe reprocessing. Normally what we try and look for is alignment issues. Since we're trying to maintain the multiples and all the other elastic effects in the data, we really don't like having a harsh radon applied on the data, but just more of alignment issues, and sometimes a very subtle radon because we might be getting influence from above the window. But normally we try to be very careful and very delicate with our preconditioning. So the porosity and permeability matches are excellent that are coming straight from the kappa, and the geomechanical results are pretty adequate. Here's the Young's modulus and the Poisson's ratio, which is quite flat. It would benefit from an improved M, which goes back to the issue of actually looking back into the alignment of those gathers. But I wanted to try and test it, just taking the data off the shelf from the public repository and throwing it into WebAVO. From stack seismic data, we can actually obtain porosity and permeability to a decent degree. That would be very helpful. And pre-stack data would be required, of course, for geomechanical parameter derivation. And with that all said, here I just have a handful of summary and observations. The first one is we should remember that WebAVO is not an extension of any Zoprist-based AVO inversion, but it's fundamentally a different approach. The compressibility is about 3 times more sensitive to fluids than acoustic impedance, And the shear compliance is truly insensitive to fluids, since it's the inverse of the shear modulus. So it's giving us the real lithology versus the fluid effect separation. Elastic wave phenomena within the window of interest, within the window of inversion are considered. So a well-known challenge that we spend a lot of time and money trying to take them out turns actually into useful data for our scheme. WebAVO also extends the spectrum on the lower side, which means we can use low frequency models, which makes us less dependent on them. There's always issue on which frequency model to use, what frequency to cut it at, etc. So this helps us out by by decreasing the dependency on these input LFMs. And WebAVO can improve the reliability of inversion cubes for geomechanical purposes, just because we don't need the pesky density from an inversion to be able to calculate Young's modulus, and because we're including all the fun and exciting elastic wave propagation phenomena in the inversion itself. And with that, that's all what we have for you today. Thank you guys for your attention. And should we go ahead some of the questions, Raleigh?
Yes, thank you for your talk today, Hansel. It was very interesting. We will take questions. If you want to type them into the questions tab or in the chat tab, that'd be great. I had a quick one I hadn't written down yet. I was wondering if you could comment on the vintage of the onshore Zagros Mountain seismic data set. Just
it was a modern data set. I mean, Panos, if you remind me, you ran the proposal for this one. Was it 2000 and I think it was at least 2010.
I can't really remember.
I don't think it's not like 2018 or anything, but it's definitely at least 2010. And the data was adequate. We did need to do a touch of a radon, again, very delicately, but for onshore data, it wasn't spectacular, but it wasn't dreadful either.
Okay. Okay. Yes, Jan, we'll have a copy. Well, we'll have this presentation recorded that you guys can follow up on, and it should get posted to YouTube, hopefully within the week. So hopefully that addresses your question. That was from Jan Dodson. So.
Hey Hansel, I got a question. Have you guys seen an increase in prospects of work done in the geothermal space? Is that something that you're seeing an increase into, or is it stable or equivalent in terms of the amount of activity you're seeing for geothermal?
Well, at least in the Netherlands, there's a lot of activity going on, and Panos can probably speak a little bit more to that.
Yeah, I think there is increased interest in geothermal, as is the last few months in carbon capture storage. But in terms of projects and work done in that domain, I would say that we're just entering the arena. So it's early days for technology there. And of course, the big hurdle there is the difference in margins of the operators. So throwing high-tech technology into something that does not have the budgets for that is the real challenge. But as Hansel nicely presented, we're trying to get that good 80% out of the technology in order to add lots of value into geothermal.
Thanks.
Yeah, geothermal is something that I personally want to look more into. I think that we can add a lot of value, and especially on the geomechanical side as well. You know, they're injecting water back in. We know what happens when you inject water back into the wrong spot and you're not aware of it. So I think that a lot of regulators and just investors would want to make sure that any geothermal endeavor is not has all that under control.
Have you? Well, I would say some operators are that are focused on kind of these source rock plays are starting to pull out some AVO-based inversion products that are giving them value, and I wonder if, I mean, based on what you've shown, it seems like the web-based inversion web-based AVO would be even a bigger uplift, just facing the compressibility and kappa.
I agree, definitely. We see that it would be a bit of an uplift, and we're trying to find partners and to be able to, or people to be able to try and do feasibility studies on that regard. But yeah, I mean, I've seen, as soon as I saw, I think I mentioned, I looked at the coals and the high TOC shale. When I looked at, we were looking at a project in Malaysia, and I'm like, okay, that is standing out. That would be very, very useful if we could apply it back in the States somehow. But yeah, we theoretically, and I mean, not even theoretically, just with what we've done with current data sets, that would definitely be able to give an uplift. Jan, I just saw your comment. I'm like, yeah, that was the point that I wanted to drive, that off the shelf. We didn't spend 12 months reprocessing and printing up the data. We just threw it into the algorithm and see what we could get and how much value we could get. And this is a project that's actually that we're doing with other areas in the Netherlands as well. So we should be publishing about that. Not only the CAG, but further after we have a little bit more meat on this topic to be able to go around. Hi, Jaime. I just saw Jaime is asking a question. Please, could you elaborate on the use of wavelet libraries and the generation of your initial model? Do you use statistical wavelets? Do you consider the wavelet to be spatially and time variant? That's a big question, but let's talk about usually the initial wavelet. We always try and do a fully elastic deterministic wavelet. And Peter, you can interrupt and explain the wavelet extraction procedure, because I didn't put that here as it was more of a higher level talk. But we normally go with a fully elastic deterministic wavelet procedure, and then we do try statistical wavelets as necessary. If we start to see that the wavelets deterministic wavelets are being too local to the area, then of course we go with statistical wavelets. But we always use the deterministic wavelets to be able to get the scalars for each of the different slownesses, and that's something that I didn't focus too much on this presentation. We don't use angle here. We use actual slownesses, which is a bit more, I guess, more correct from a physical perspective when you look at it. So yes, we use statistical wavelets. We always start off with a deterministic wavelet and then assess from there. And we don't vary the, well, has there been any case, Panos, where we have varied the wavelet spatially? Time variant, we always try not to, because if we have to go ahead and we actually just working on a project that has a very large window, and we had to optimize the wavelet for the upper, middle, and deeper reservoirs. But spatially, I'm not sure if we've done that before I got here.
Of course, yeah, you can have many wavelets and try to have some kind of interpolation between wells. That's depends really on case by case, how much variability you have laterally. Sometimes it does make sense to do that, but definitely you would like to have as less bias on your wavelet as possible. So either going statistical or getting one wavelet for the full region, that would be the best way forward, I guess.
Thank you, Panos. And for the generation of the initial model, I just saw the other question. Sorry, Jaime. Well, it depends. We normally try and separate these projects into feasibility, so we have a smaller cost and just be able to make sure that the inversion is giving us what we need. So what we do at that case is that we use well logs and interpolate the data with horizons, which of course is not optimal. But then we go ahead and use collocated co-kriging. We use, if we have full waveform inversion or PSTM velocities, we use those and try and calibrate that as well in the model. I mean, with the low frequency model, there's a lot of rinse and repeat. I think what's more important about the initial model is to picking the right frequency, and we do run tests and to be able to, because I mentioned the initial models are maybe a little bit less less frequency than conventional ones, which is good because we're not as dependent on them. But we always just do run those a lot of those tests. So does that help? Initially, we start off with a well and horizon based model, and then we complicate it as we need as the project goes along. And Panos and Peter, can interrupt me at any time, by the way, please.
I think it was a rather complete answer. The only point that I would like to highlight again, and I think you mentioned during your presentation, is that although we need an initial model, one unique aspect of the technology is that we are less dependent on the initial model. So we're not completely independent of an initial model, but we have the technology has a chance to make up for any inaccuracies in the initial model. So that's a unique aspect of the technology, let's say.
Okay, we got another question. Do you see this wave equation-based AVO used as a depletion tool for onshore tight gas plays due to the kappa sensitivity?
That's a good one, Jason. It definitely would work. Well, in the 4D sense, we're doing that right now. And on tight gas plays, I mean, I think that would actually be theoretically be very easy to do that. The way that kappa jumps with your gas saturation. I don't think we've had that particular case so far. Guys, correct me if I'm wrong, but yeah, definitely that could be a very cool tool to measure, to map that depletion, particularly in a tight gas play where you can't really see a lot more if you're looking at AISI or Lander or Muro.
Well, exactly. That's the space where you would see the uplift coming from the parameterization, because where acoustic impedance wouldn't be able to help you find the difference in saturation, then compressibility would help.
Yeah, if I may add, I think it was one of the very first case studies that we performed, and we got a set of logs, and back then we also looked at acoustic impedance, shear impedance, and they looked all very similar. But then we looked at kappa, and kappa was that different that we had no idea what is going on there. So we spoke to the operations team, and they confirmed and they reported that the reservoir is depleted over there. So that was really a kind of a highlight where you see compressibility working very nicely in this context. But I'm afraid the case study is a bit older, so it doesn't make it into the slide deck anymore.
Jaime has another question. Have you used PSTM data on your workflows? Yes, we have. We use PSTM. We've used all sorts of data, including very old onshore 2D data, just to try and get a kappa and such. And yes, we have. You're correct, but that we are still been able to get successful projects with PSTM. I don't know if you want to add any comment on that one, Peter.
Anybody have any other questions? Checking the other side.
Thank you, Tim. We appreciate your comment.
Okay, guys. I guess we'll call it. I really appreciate you taking the time to present today and join us from all over the world. That's pretty exciting for OCGS. And if anybody has any other questions they want to follow up, you can see their email address there and their website. So don't hesitate.
Just send us a note on LinkedIn. We're happy to chat. Thank you all. Thank you, Raleigh. Thanks, OCGS.
Thank you all.
Thanks, guys.
Thanks, everybody. Bye-bye.
Cheers.
Thank
bye-bye.
you.